Good morning all, welcome back to Chem Connect. I hope the Diels-Alder reaction basics that we have discussed in last week is clear to everyone. Today we will be discussing regarding the regioselectivity in Diels-Alder reaction. Coming to the regioselectivity of Diels-Alder reaction, this is the dienophile we have been using in the Diels-Alder reaction. This is the typical Michael acceptor that we have seen previously. It will undergo 1,4 addition reaction of the nucleophile to give this enolate, which upon reacting with proton, it will give this 1,4 addition product. Why is this fourth position reacting rather than the 1,2 position? This is because of the presence of the carbonyl group. The orbital, the energy of this LUMO is lower, as well as the orbital contribution at this 1,4 position is greater. So the nucleophile will be approaching and reacting with this p orbital at this position. So as we can see here, for this dienophile, it is lower in energy. The 1,4 position or LUMO is lower in energy because of the presence of this carbonyl compound, and it is having unequal coefficients. Because of the unequal coefficients, the orbital contribution at this 4th position is greater, and the nucleophile will be coming and reacting at this position. When we compare it with a normal alkene, you can see the energy of the LUMO is higher, and the coefficients are of same size. That is why this is preferred for Diels-Alder reaction. For better reaction to take place, we know that the HOMO should be higher in energy and the LUMO should be lower in energy. Now if we consider 1,3-butadiene, it can react with HBr either by the attack at N carbon or the attack of the middle carbon. When it is attacking HBr from the N carbon, it will result in the formation of the stable delocalized secondary cation. That is, this double bond can be delocalized into this cation so that it will be delocalized, and here the secondary carbocation is resulted, which is more stable. And if we consider the reaction of middle carbon atom, then if the middle carbon atom go and attack the HBr, it will result in the formation of this primary cation. It is not delocalized as the double bond is one carbon away from it. So, the formation of the stable delocalized secondary cation is more favored in this case of 1,3-butadiene. And we can see that if we consider the molecular orbital picture, the orbital contribution of the N carbon is more compared to that of the middle carbon. That is why the N carbon can react with the electrophile when we consider the case of this 1,3-butadiene. Now, coming to unsymmetrical diene, here the attack will take place from the N carbon. So it will result in the formation of this carbocation. It is a secondary carbocation, and once it will get delocalized, it will result in the formation of a tertiary carbocation. So we can see the more stable allyl cation, which is delocalized between a secondary and tertiary carbons. Now, if we consider this N carbon is reacting. If this N carbon is reacting, it will result in the formation of a secondary carbocation. But when it will delocalize, this double bond will delocalize to this cation, it will result in the formation of a primary cation. So compared to this case where the allyl cation is delocalized between secondary and tertiary carbon, here it is delocalized between secondary and primary carbon, which is less stable. So this case is more favorable. And we can see that in the case of 1,1-dimethylbutadiene, the orbital contribution of HOMO is greater at this position. So this N carbon is more favorable for reacting. Now if we consider both this unsymmetrical diene and this unsymmetrical dienophile reacting, we have seen that the orbital contribution at this carbon is greater, and for the diene the orbital contribution at this carbon is greater. So it is more probable to react together, resulting in the formation of this transition state where a bond is formed between these two carbons, and it will result in the formation of a negative charge on this carbon and a positive charge on this carbon because of the shifting of the electrons, and this will result in the formation of a new bond here, resulting in the formation of the cyclohexene. Is this clear? So, when the unsymmetrical diene and the unsymmetrical dienophile combine in a Diels-Alder reaction, the reaction will also become unsymmetrical. It remains concerted, so it will take place in one step and it goes through a transition state. Bond formation between the largest coefficients in each partner is more advanced, and this determines the regioselectivity of the reaction. So we can see here the greatest or largest coefficient for this dienophile is this carbon, and the largest coefficient for the diene is this carbon. So these two carbons are more probable to react, and it will result in the formation of this product regioselectively. Now coming to mono-substituted diene. So the outcome of the product depends on the carbon where it is substituted. So the diene can be substituted at first carbon or the second carbon. So the outcome of the product will result upon which carbon is substituted. So when we consider the two classical cases where the electron donating substituent could be present at carbon 1 or carbon 2. So we are considering the substituent to be electron donating, because when the substituent will be electron donating, then the diene will become more electron rich. So we have one substituted diene and two substituted diene. Now we will see what will be the product or outcome of the product when it is one substituted diene and when it is two substituted diene. Now coming to the case where one substituted diene is reacting with the dienophile. As we can see here, when it is one substituted diene, so it will be electron releasing inductively. R group will be electron releasing inductively. So the more electron rich carbon will be here. You can see this will be the more electron rich carbon, and in the case of this dienophile, this E is an electron withdrawing group, and this will be the carbon which is electron deficient. So this electron rich carbon and this electron deficient carbon is supposed to react, and it will result in the formation of this 1,2 product as the major product. And the other case where the dienophile is oriented in this fashion, it can result in the formation of this 1,3 product, but this probability is much lesser because the electron rich carbon of the diene and the electron deficient carbon of the dienophile are supposed to react, and we will get 1,2 product as the major product compared to this 1,3 product. So is it clear? When one substituted diene reacts with the dienophile, it will result in the formation of 1,2 product. Now, so for the preference of 1,2 product can be explained by considering the polarization of the diene and dienophile as we have seen in the previous slide. So we will connect the electron rich center of the diene to electron deficient center of the dienophile. So this is the electron rich center of the diene as we have seen in the previous slide, and this is the electron deficient center of the dienophile. We should consider this R is an electron releasing group and this is an electron withdrawing group. So this will be the electron rich center and this will be the electron deficient center. So the electron rich center and the electron deficient center, it is supposed to connect, and it will result in the formation of this 1,2 product as the major product. Now coming to two substituted diene. Now we have seen the case of one substituted diene. So there are two possibilities, 1,2 product or 1,3 product. We will get 1,2 product as the major product because we will connect the electron rich portion or electron rich carbon of the diene and the electron deficient carbon of the dienophile. Now coming to two substituted diene. So this is the electron releasing group. So this will be the electron rich carbon and it is the electron deficient carbon. So the electron rich carbon and the electron deficient carbon will connect and it will result in the formation of this 1,4 product. And if we consider this case where this electron rich carbon is not connecting with the electron deficient carbon, it will result in formation of 1,3 product, but the formation of 1,3 product will not take place and we will get exclusively this 1,4 substituted product. So this is the electron rich sender and this is the electron deficient sender that should connect and we will get 1,4 product as the major product. So we have an example here. So we are given an R group, that is the OMe, which is 2 substituted, and we have this cyano group as the electron withdrawing group in this dienophile, and what will be the Diels-Alder product. So we can see that this is the electron donating group and this will be the portion or the carbon where this electron rich sender is present. So this will react and it will add to the electrophile. And in the case of the dienophile, this is the carbon which is electron deficient. So it can react with the nucleophile. So here in this case, this carbon should connect to this carbon and the Diels-Alder reaction will result in the formation of 1,4 product as the major product. So we should consider the case of 2 substituted diene reacting with a dienophile and we will get 1,4 product as the major product. So concluding, we can say that if X is an electron donating group such as alkyl, aryl, OR, Me3SiO, R2N, etc. and Z is an electron withdrawing group or conjugating group such as CHO, COR, CO2H, CO2R, CN, NO2, halogen, alkynyl, aryl, etc. So, in the case of one substituted diene, it will react with the dienophile in this fashion, where this is the electron rich carbon and this is the electron deficient carbon, and we will get 1,2 product as the major product. And in the case of 2 substituted diene, it will react with the dienophile in this fashion, where this is the electron rich carbon and this is the electron deficient carbon, and we will get the 1,4 substituted product as the major product. So this is the useful mnemonic that we can use. If you prefer a rule to remember, try this one. So the Diels-Alder reaction is a cycloaddition with an aromatic transition state, that is ortho and para directing. So in Diels-Alder reaction we will get either ortho product or para product. If the diene is 1 substituted diene, we will get 1,2 product as the major product, and if the diene is 2 substituted, we will get 1,4 product, that is para product as the major product. Now we have one practice question based on what we have studied today. So which of adducts A to D is the main kinetic product of the following Diels-Alder reaction? So here this is the electron releasing group. So this will be the electron rich sender and this will be the electron deficient sender. So we will get a 1,2 substituted product. So we can rule out these other options. Okay, and here the dienophile is substituted with a carbonyl group. So it will result in the formation of endo product. And here in the case of this diene, this is outward, and if we consider the bottom phase approach of the dienophile, if the OPH is pointing outwards, it will be alpha, and the hydrogen which is pointing inwards, it should be beta. So this OPH will come as alpha, and if we consider the endo approach, the CO2 Me group will be coming inwards. So it should also be alpha. So the right answer for this question will be option C. The right answer for this question will be option C. I hope whatever we have discussed today regarding the regioselectivity of Diels-Alder reaction is clear to everyone. If you have liked this video, please like, share and subscribe. Thank you so much.